So for your exam 1 and 2 stuff, it's not a ton of problems. It's good to work because it'll help you prep for the final anyway, and I'm actually going to let my current students do these same problems to kind of get some extra credit on their exam grade, and like it'll help prep for the final. But basically what I've done is this file is already on ELC. What I recommend that you do is print it out in hard copy, and then when you watch the review video, which I'll finish recording this evening, you want to go through it with me, and then in like a day, about 24 to 48 hours, I'll have the exam 2 content up. But I pared it down to just 4 sections because this is the essential stuff that you need to know for Calc 3 if you have to integrate and stuff. So basically what it is it goes section by section. I've got notes, I've got problems, I put diagrams in here, and then I will go through on the video and fill this in. So basically this is designed so when it's done, you have a nice complete set of content from Unit 1 and Unit 2 that then if you're in Calc 3 and you need to revisit it. And what I'll do is I'm going to hide the videos on YouTube, but at the end of the semester, I'm going to send you guys the links to the playlist. So if you've got the link, you can find them. But if you ever need to go back and rewatch or revisit any of this stuff, like when you're in Calc 3, you'll be able to. But like it just kind of goes section by section. I got really good diagrams in here, so we'll annotate it. But we'll just go and you can see you've got all your formulas. I'll explain all the proper methodology to solve the problems. I tried to pick things that aren't too insane, but just so you can make sure. But like shell, you guys didn't do anything really meaningful on shell method. And then you can see like I'll explain like why the methods work. So it's pretty awesome, I think. I worked really hard on it. So you'll have another one of these for the exam 2 content, because the exam 2 content is going to be all the different types of integration techniques, because when you get into Calc 3, you'll be dealing with 3D coordinate systems, and you'll be changing to spherical and cylindrical coordinates, and those involve a lot of trig. So it's really important that you guys review the correct way to do all the trig integrals, because you will be integrating trig functions. They're not as bad in Calc 3 as they are in Calc 2, but you still need to know how to figure this stuff out. So that'll be available for you guys. So I'll finish recording it tonight. Like I said, the file of this is already online. You can download the file, print it out. But I just recommend printing a hard copy and just following along and filling it in with me as you go. So one of the tricky things on this stuff is drawing the pictures. So I tried to make sure I found problems where it was not like, it was not super hard integration, but like kind of the basic ideas you needed to know. And then I had like good diagrams so you could visualize the rotation and see what this stuff is going to look like. Because when you get into Calc 3 and you start doing 3D problems, you're going to have to know how to sketch things in the 3D plane. And so if you've kind of got a good base on how to do this in Calc 2, you'll be a lot ahead of the game for Calc 3. So, and then of course, I will be working with Milledge Hall next semester, but I won't be in there 20 hours a week anymore. But I'll be really involved with our study hall, and technically anything beyond Calc 2, you should be using the Boyd study hall anyway. So you guys can always email me if you need to come in there and work, and I can tell you what nights I work in the study hall for those shifts. All right, so we won't be here the whole time today because we were able to knock this out in less than 50 minutes in my last class, so we'll just bounce when we're done because I know it's finals week and y'all have a lot to do. All right, so, and you're welcome for canceling class on Friday, guys. I just got to think about it. I was like, it's going to be rush hour. I knew everybody's going to Atlanta. I was like, I would not want to be in rush hour traffic. And I was able to get the 2 classes lined up, and I was like, we're going to do literally verbatim what we did in the other class. So I just didn't see the point in making everybody sit here till 4:45 on a Friday. All right, so today, what we're going to do, and this is where you're going to realize that your algebra skills are crucial. So we're going to look at applications for Taylor and Maclaurin series. So remember, the only difference between these two is that a Taylor series can be centered at any value we want to center it at, but a Maclaurin series is always centered at 0. All right, so the first thing, right, we looked at last time, we were like, okay, how do we build one of these from scratch? And we saw we had to take multiple iterations of the derivative, then we had to find those coefficients, plug it in, and generate the series, right? But what we can do now that we actually know how that's done, we can see that there's a couple of other techniques we can use so we don't have to go through all that, because some of these derivatives can just get really disgusting if you keep having to do the product rule again and again or the quotient rule again and again. So we can actually recognize functions that exist inside other functions and do this pretty easily. So let's start with something really basic, right? And that is the geometric series. So we saw like early on the geometric series is of the form a times r to the n. And we know that this guy converges whenever the absolute value of r is less than 1. A can take on any value we want because it's just a constant. Furthermore, we saw that if we're summing it from 0, we proved that it sums to this. And so this is all okay as long as this is true. So what if I wanted to write the Taylor series for this function? So this derivative isn't too terrible. We actually did this one in a previous example, and so we saw, well, we could write it as 1 minus x to the negative 1, and we could take a couple derivatives, and we would see that it's going to alternate back and forth. All right? But the form of this series, if we look at it, actually this one isn't going to alternate, we could see that the form of this series looks a lot like 1 over, or a over 1 minus r. Okay? So if a over 1 minus r is simply the sum of this, we can actually extrapolate and work backwards. So what we have here is a geometric series where a is 1 and r is just x. So we can write this as the series of 1 times x to the n. And so if we expand this out, right, it's just going to look like this. So there would be no reason to take this guy from scratch. So let's look at something a little more complicated that we can actually turn into a geometric series. So if we look at the function f of x over, or f of x is 4 over 2 plus x, right? So if I can rewrite this in the form of a over 1 minus some expression in x, then I can rewrite this as a geometric series. So what we could do is first we could say, well, I need a 1 in this denominator. And in order to get a 1 in the denominator here, I need to factor out a 2. So if I factor a 2 out of the denominator, I'm going to get 1 plus x over 2. So if you distribute that back, you'll see those are equivalent statements, right? So I can also say, well, that 4 will divide by 2, so I can change the numerator to a 2, right? But the denominator, we need to do one more tweak on it, because the denominator isn't supposed to be 1 plus something, it's supposed to be 1 minus r. So to write this as 1 minus r, I can say, well, that's the same thing as saying 1 minus negative x over 2. Everybody see that? So if you can always check your algebra by just undoing it, you should get what's just came back. So now this is the form of a over 1 minus r, where a is 2 and r is just negative x over 2. So if I want to write this as a geometric series, I'm not going to write 2 over this. I'm going to write my original function, 4 over 2 plus x is now just the sum from 0 to infinity of a, which was 2, r to the n. If you did this out the long way and actually took the derivatives and found the coefficient and wrote this out, you would see that this would in fact give you this exact series. Now we would typically take this one more step out, but I'm going to show you that on the next problem. We usually don't like to write, we can write negative r's in here, that's fine, but we know that this converges if r, the absolute value of r, is less than 1. So this will converge as long as that is true. So then if we wanted to find the radius of convergence, we could. If we wanted to find the interval of convergence, we could do that. Now remember, on a geometric series, we talked about this back when we did the interval of convergence, they never converge at their endpoints. Because if you set this equal to 1, what you get is 2 times 1 to the n, and that's just 2, 2, 2, 2, 2, 2, 2, and that will never converge. So geometric series are never going to converge at their endpoints if you test them for convergence. So what were these two centered at, those two series? Right, you should always be able to see the center when you look at it in the series form. 0, right? Because it was just x to the n or x over 2 to the n. Because you'll know its center because it'll always have the form x plus or minus c, right? And so if you can't see the c, that means the c was 0. So both of these series were centered at 0, right? So we can actually do this for a series centered at 1. So if I wanted this guy, if I wanted to turn this into a geometric series, you're actually going to see in order to use a geometric series here, we kind of have to center it at 1 because we can't come up with the proper form. So if we look at this, this sort of looks like 1 over 1 minus r, right? We've got a 1 on, or a over 1 minus r, a would be 1, but we need to manipulate the denominator to get it of the form we want. So if we take 1 over x, and I want to put a 1 minus right here, my r value, well, that x is positive. So that means inside my parentheses here, my x needs to be negative. And so the rule in algebra is, right, you can do whatever you want. If you're solving an equation, you can do whatever you want as long as you do it to both sides of the equation. But in this case, we don't really have another side of the equation to manipulate. We're trying to rewrite it. So the other thing you're allowed to do is you're allowed to add 0 to anything you want because it just returns itself. So if I add a 1 here, right, this is actually 1 plus x if I expand this out. And that's not what this equals. So if I want to make sure that it's equivalent to just x in the denominator, I have to subtract a 1. But because of this negative sign right here, it's really going to add a 1. So if you distribute the negative sign, what you'll get is 1 plus x minus 1. Which is just x. So this is an algebraically equivalent equation. So the other thing I need to do here is, well, when I want to see the center in the series, the center needs to be x minus c, okay? So if I'm looking at this guy, we are of the form a over 1 minus r, where a is 1 and r, right, is negative x plus 1. But if I'm centering this at 1, I need to turn this into x minus 1. So how do you reverse the order of subtraction? So you technically aren't allowed to multiply, that would do it, but you're not allowed to multiply by a negative 1 because that would change the value. So what we do is we factor out a negative 1. Okay? So if I factor a negative 1 out of this expression, I get this. And if I multiply the negative 1 back in, it does equal the original thing I started with. Do I see that? So if you ever need to flip the order of a subtraction, you just factor out a negative 1 and it reverses the order. So now I have my a and my r, and I can now express this as a geometric series. So my a was just 1. My r, right, was negative quantity x minus 1 raised to the n. Now, typically, we wouldn't leave it like this. This is a little cumbersome, and since we're totally comfortable working with alternating series, hopefully we are by now, remember, if you have something times something else raised to the same exponent, I can rewrite this as negative 1 to the n times x minus 1 to the n. So this is a alternating geometric series centered at 1, and you can always see the center in the equation. So this will converge, right, whenever the absolute value of x minus 1 is less than r. So it's whenever the absolute value of your r value is less than 1. Right? So does anybody notice a pattern in these three examples we did? Like what was going on in the numerator and the denominator? Look at the functions. What were all the numerators?
Constants.
Constants. What were all the denominators?
Variable expressions.
A specific variable expression, though. What was the power of x? They were lines, right? So if you have a function that you're trying to write a series for, and you have a constant over a line, then you can write it as a form of a geometric series. Algebra will always allow you to put it in the form of a over 1 minus r. So we saw with the one above where we had that 2 plus x, if we pulled the 2 out, that created the 1. Okay? Now we got to be careful because we want to make sure that we only factor out the 2 or the constant in the line to get the 1. You are allowed to have some stuff attached to the x, okay? So if your slope was like, if you had 2 plus 3x, right, this would still work. You would pull out the 2, and then you would get like 3 halves x, okay? And so 3 halves is a fraction bigger than 1, but if you plug in x values that are bigger, or excuse me, are small, and make it turn into something less than 1, it's still possible for it to converge. So whenever you see a constant over a line, it is a form of a geometric series. So let's look at some algebraic properties we can work with series. So these are both going to be power series. These are two different functions. And so if you notice what's different in the series is I've given you different constants, right? So whenever we figure out the coefficients, we'll have some a sub n expression will be the coefficients for the first one, and some b sub n will be the coefficients for the second one. These two series are centered at 0. If you want to use these operations, the series really do need to be centered at the same value for you to be doing this. So that way you can factor out the x term in the correct way. So these are the three main operations we can do. We can say, well, if I want to plug in a constant number times x, well, if I had a function f of x and I wanted to plug 2x in, well, then I just replace everywhere I had an x with a 2x. Same thing's true in a series. You would take the series, a sub n is a coefficient, it's just a constant, so it's still there. But when you plug kx and raise it to the n, that is the same thing as saying k to the n, x to the n. So just like we were able to factor out the negative 1 in that previous example, we could factor out a k. We could also plug in x to the capital N. So capital N here stands for some constant power. So like this would be if we wanted to do f of x squared or f of x cubed, okay? Well, if you did this with a regular function, right, you would just plug that in the place of every x. Well, you can do the same thing for the series. You can take the original series that you started with and just plug in x to the n. Well, when you raise a power to a power, you multiply their exponents together. So if this were x squared, that would become x to the 2n. If it were x cubed, it would become x to the 3n. We can also add and subtract known series. So if we want to do that, well, since they are both just coefficients multiplied by x to the n, you can factor the x to the n out, and your new series is just the sum or difference of the coefficients times that x to the n. And that's why I said if they're centered at the same value, this is a really easy step. Notice here, these are the only three operations. Notice there is no operation for multiplying series together. And we're gonna actually talk about that. We'll do an example at the end of how do you get around that. Sometimes you can do it directly, and sometimes we have to use a tricky substitution. All right, so let's look at an example of finding a series that doesn't look like a geometric series, but by employing some of these rules, we can make it happen. So we want to find the power series for this centered at 0. So this is a great example of a problem where you would have to do the quotient rule to do the derivatives, and that would just get really gross really fast. If you had to do the 4th, 5th, 6th derivative, it would just get disgusting, okay? But if we can figure out a way to rewrite f of x in terms of other things we know, we can sort of backdoor sneak in and build the series by summing up other stuff. So if we have a constant over a line, we know we can do the geometric series, and those are really easy. But what we have here is a line over a quadratic. So in Unit 2, we did something called partial fractions, which you'll see in detail on your video. But what we can do when we have partial fractions is what you're supposed to do is take the function and expand out the denominator as far as you can. And this is a difference of squares. So the denominator will factor into x plus 1, x minus 1. So all of those factors, right, what we are looking at is a function which was probably the sum of two fractions, which we don't know, and once we found the common denominator and added them together, it's simplified to this. So what you were doing with partial fractions is you were taking an equation that had already been completed and you were sort of working it in reverse. Try to find, well, what did you add up, okay? So because those terms are linear, right, that's great for us because that means we can probably use the geometric series. So this turns out to just be 2 over x plus 1 plus 1 over x minus 1. And those are in fact of the form a constant over a line. So we're going to call this guy number 1 and this guy number 2. So what I'm going to do is I'm going to build the geometric series for each piece, and then using that third algebra rule we have, we can add the two geometric series together to give us the series for our original function. So if we look at the first one, 2 over x plus 1 is the same thing as saying 2 over 1 minus x. So that is of the form a over 1 minus r, right? Our a would be 2, and our r would be negative x. So if I want to write it as a geometric series, a is 2 times negative x to the n. Ideally, we'd probably take that out one step further and write it as 2 times negative 1 to the n, x to the n. And the reason I want to factor the negative out is because I know I'm going to have to combine this with another geometric series. And if I just have it written as x to the n, it's going to be easier for me to factor that out. I don't want to deal with a negative sign. The second one is a little bit easier because we're mostly there already. So I've got x minus 1, but I need it to be 1 minus something of x. So I can reverse the order of subtraction in the denominator by factoring out a negative 1. So I'm just going to move the negative 1 to the denominator, the numerator, excuse me. So I just have negative 1 over 1 minus x. So I could have written it out in the denominator out to the side, but 1 divided by negative 1 is negative 1, so it's just easier to move it into the numerator. So now what we have is a negative 1 is our a, right? And our r is just x. So here's where you want to be careful with this. The -1 in the numerator is not the same thing as what was happening with the -x in the denominator of the previous problem. The negative was attached to the x and it had to be raised to the n. But a is just a coefficient, and you're allowed to pull a coefficient outside of the summation, just like you're allowed to pull it outside of an integral, right? We pull it outside when we're taking the derivative. So I can actually write this as a geometric series as -1 times the sum of just x to the n. And the reason I didn't want to put it inside the summation is I didn't want anybody to get confused and try to raise that thing to the n, because it's not supposed to be raised to the n. So if we want to write the series for our original function, well, we can simply use this rule right here. We can say, well, we'll take this guy and we'll add it to this guy. And since he's negative, we're really going to subtract them. So the original series, 3x minus 1 over x squared minus 1, is the sum of 2 to the -1 to the n, x to the n, minus the sum, right, of x to the n. Remember, addition and subtraction are the same thing. We're just adding negative things. So I can factor that x to the n out and write it as one single series where the coefficient is 2 times -1 to the n. That's what I get when I factor out x to the n. And over here, when I get factor out x to the n, I'm just left with a -1. And so this guy is centered at 0, and that is the series for the first one. So even though this seemed like it was a lot of steps, it was much, much faster than trying to take the quotient rule again and again and again and again and simplify and to get the derivative. Any questions on this other than you guys probably don't know how to do the partial derivative part, but that's okay. The partial fraction part, but I'm gonna show you guys that. It's not that hard to do.
Perhaps the question would have been more fitting for earlier stuff. I've been thinking about this wrong. I still don't fully understand the value of Taylor polynomials / series. I don't understand why we're doing it. I get it's helpful for something. I just don't understand what it's helpful for.
Okay, so let's say, and I'm just, my guts to go to physics just because I know a lot about physics, right? So in physics, right, a lot of these functions could be position as a function of time, right? And you might need to know the speed, the acceleration, right? And in physics in general, there are a lot of variables that are related to each other by the derivatives and their integrals, okay? Rates of change. So if you are working with a complex equation in physics, and let's say we only have to be accurate to like 1%, okay? Well, that means if I can write it as a polynomial, I only might need 2 or 3 terms of the polynomial. It is super easy to integrate and differentiate a polynomial as opposed to working with the original functions, right? You're going to see in a minute, we're going to do some trig equations. And when you're talking about waves, like light as a particle and a wave, and when you're talking about waves and photons and things like that, well, those wave equations, it's very complicated to take the derivative and integrate and all that stuff when you're dealing with those. But 3 terms of a polynomial will get the job done for you. So when you're integrating and differentiating and going back and forth, it's much, much easier to work with the Taylor series. So physics uses this all the time. And then the other example of this we talked about would be sometimes in computing, right? If you're trying to do complex computing, once again, if you know the accuracy you need, you don't actually deal with the infinite series all the time. You just need to know how many terms you need to go out. So you might be able to generate a polynomial of degree 5, and that's very easy to work with and very easy to use. So work is the integral of force. So if you're integrating, it's much easier to integrate a polynomial. So if you can take the force equation and turn it into a polynomial, you're home free, right? Momentum is, I think, the derivative, or is it the integral of force? But momentum and kinetic energy are related. Yeah, that's what it is. Momentum is the integral of kinetic energy. So if you're talking about energy versus, so when there's, in physics, when you're trying to measure lots of different quantities about the same thing, if you can turn the original function that you write into a series, a Taylor series, and every physics book on the inside cover, when, you know, beyond the intro level, literally has a box of the most common Taylor series written out for you to use these guys. They're really useful.
Okay.
So anything where you're integrating, and we're actually about to show you there's another way you can build a Taylor series that's really sneaky by using the relationship between a function and its derivative and vice versa. So they're extremely useful. We use them a lot. But yeah, I took an optics class, and in optics you're just dealing with light. Well, light's a wave and a particle, and so we were doing tons of wave equations. And when when you actually look in the real world and you have anything vibrating, it acts like a spring, and so you get a lot of like complex wave equations that you have to deal with, and we would use Taylor series all the time because we took derivatives, and calculus was sort of invented to do physics problems. I mean, they had all the theories, but the calculus actually proved how to do it. And once you see something has the relationship between its derivative and the original function, everybody gets excited. And so momentum, which I know a lot of you guys don't know about in here, but momentum was a 20th century concept that Einstein came up with because he noticed that that mv, so he decided, so that's what momentum is, it's mass times velocity, had a relationship back to force. So momentum is actually Einstein's interpretation of Newton's second law, which is just mass equals force times acceleration. And so that was actually a 20th century idea where they tied two, and that's why kind of we don't have cool units for momentum because they're too new and nobody came up with a cool unit for it. All right, so let me show you another kind of neat way you can do this, and this is going back on your question, why would you use a Taylor series, right? Because you can't do this as easily with the original function. We just showed that 1 over x can be written as a geometric series centered at 1. We just did this one, okay? But let's say that I want the power series for ln of x centered at 1, okay? Now, we can technically center things around any value we want, but a lot of times when you see these guys generated, the most common center used is a known value on the function. So centering ln of x at 1 makes a ton of sense because everybody knows the natural log of 1 is 0, right? It's an easy thing to compute. So what is the relationship between ln of x and 1 over x? 1 over x is the derivative of ln of x, okay? So if you know that ln of x is simply the integral of 1 over x dx, and you know the power series for 1 over x, you can just integrate the series. Because the reason you can integrate and differentiate these power series is because they're just polynomials. So it's just a power rule. It's easy, okay? Now, one thing to keep in mind, the function is of x, that's the variable, right? And the integral, the variable, is x. So that's what we're going to integrate with respect to. However, the series is indexed by n. So anything involving an n that doesn't have an x term in it is just treated like a constant when you're integrating. So these things are actually quite simple to integrate. So if we look at this, and I want to integrate the series, well, the negative 1 to the n is just a constant, so it just stays right where it is. But x minus 1 to the n, I have to use the power rule. So remember, we add 1 to the exponent, and then we divide by that new exponent. And we didn't have to worry about chain rule or anything here because the derivative of the inside function was just 1. So we didn't have to worry about a u substitution or anything like that. Now, technically, we still have a constant of integration. So in order to solve for the constant of integration, well, we usually just use a known value on the original function. So we know that the natural log of 1 equals 0. So when you plug in x equals 1 into this series, you'll simply see that c works out to be 0. And that's kind of obvious to see because when you plug in 1 for x, what you're going to get is negative 1 to the n times 0. So this just becomes the sum of 0, which is 0. And 0 plus c equals 0 means c had to be 0 as well. So this worked out. And so very quickly, we were able to come up with the power series for ln of x centered at 1 by simply knowing the power series for its derivative. The converse would be true too. If I gave you natural log of x centered at 1, and I said, get me the power series for 1 over x, and you knew that it was its derivative, you would differentiate the power series. And then that would give you the power series for the derivative. All right, let's look at another one. Let's say we want the power series for arctan of x centered at 0. So if you tried to build this guy from scratch, your first derivative would be 1 over 1 plus x squared. Then you would have to take the second derivative of that function. So then you would have a chain rule, and a chain rule, and a chain rule. And then it would, by the second derivative, you'd be up to the quotient rule. And then it would just get really gross and nasty from there, okay? So it would really be cumbersome to try to build arctan of x from scratch, all right? However, we know that the derivative of arctan of x is 1 over 1 plus x squared. So I don't know the power series for that, but I do know that if I look at this guy, this is a form of the geometric series. And we actually wrote this one out. We said, well, if we rewrite that denominator as 1 minus x, we now have a power series, and this guy worked out to be the series of negative 1 to the n times x to the n. That's a very simple series. So if I want to know what the power series is for 1 over 1 plus x squared, well, I can use that second rule I gave you in series. All I have to do is plug x squared into my function, right? And now it becomes 1 over 1 plus x squared. Well, that second rule for operations for power series said, well, all you have to do to the series is plug x squared in for x. So x squared raised to the n, you multiply their coefficients or their exponents together. So that is just the series from 0 to infinity of x to the 2n. So the reason I wanted to start with 1 over 1 plus x is very simple geometric series. I could easily convert that into 1 over 1 plus x squared. And now I have the series for the derivative of the series that I want. So just like we did with ln of x, all I have to do is integrate this, and now I've got arctan of x. So if we integrate 1 over 1 plus x squared dx, then just like before, the negative 1 to the n is just a constant, so it just sits there. And we add 1 to the exponent and then divide by 2n plus 1. We still have our constant of integration. And since we're centered at 0, does anybody know what arctan of 0 is? So another way of thinking of how to figure out arctan of 0, what angle is tangent equal to 0? So make a picture of the graph. What is tangent and arctan? They both do the same thing at 0.
0.
They cross the origin. Yeah, so they're 0 at 0. So if you know that arctan of 0 equals 0, you'll see that c actually equals 0. So the series for arctan of x is in fact just this. So just like we said before, we could do this the other way. If you knew the series for arctan, you could take its derivative and come out with 1 over 1 plus x squared. So on the exam, I will definitely 100% give you a problem where I want you to build a power series off of another known power series. but I will provide you with the series I want you to build from. I'm gonna give you a problem where you're gonna have to build from scratch, like you have to know the algorithm, but it'll be something where the derivatives aren't too crazy, so you can take the derivative multiple times, because we have time constraints, obviously. But I am gonna ask you to build a series off another series, but I will provide you with the correct series that you're supposed to start working from, all right? So what I wanna show you is, like I said before, how do we deal with something when we might have to multiply, all right? So if you tried to start with sine of x and said, well, I'm going to be clever and I'm just going to multiply sine of x times sine of x and be done, well, you get into trouble, because you have to remember that the series are infinitely long polynomials. And if you multiply a polynomial times a polynomial, you have to distribute all the terms. So if you guys remember foiling, that's just when we're looking at two binomial terms, right? You have to multiply 4 things, right? You have to do first, outside, inside, last. And the more you expand the terms of those polynomials, the more distribution you have to do, okay? So it won't work to do infinitely many terms times infinitely many terms. So if you wanted to integrate sine squared, does anybody in here actually know the substitution that you were supposed to make to do sine squared? It's okay if you don't, because I doubt you do. My last class didn't know, and they were with me the whole semester. But if we wanted to integrate sine squared, we can't by itself. We also can't integrate cosine squared by itself, because we don't have a u and a du. Even if you write it as sine x times sine x, you can't turn one of the sines into cosine and vice versa if they're just single power terms, okay? So there is a trig identity that you can use to make this something more palatable. So what we do for sine squared is, if we were integrating it, we would make that substitution, because I can integrate cosine of 2x easily, because I've reduced the power down to 1. For cosine squared x, the identity, just in case this ever comes up, is this. And so what these are is, it's just an algebraic reworking of the double angle formula for cosine. So there's like 3 ways to write the double angle formula for cosine. You can write it in terms of just sine squared, you can write it in terms of cosine squared, or you can write it as a combination of the two. So whenever we have to integrate one of these two things, we replace with the appropriate guy, and then we integrate from there. So rather than building the series for sine squared x, if I can build the series of this, it is equivalent to this, all right? So what we want to do is we're going to stack this up in pieces. So I don't know the series for cosine 2x, but cosine x is famous. We actually looked at it earlier. Cosine x is even, so the polynomial you generate are only the even terms. Oh, and I just thought of another application for your question earlier. Also in statistics, if you're in any science that crosses statistics, if you have a data distribution or you're doing any kind of experiment and you have a distribution, and when you can have a computer generate the curve of the line, if the curve of the line is like a combination of trig and some crazy exponential terms, what you can do is, because when you integrate under that curve, that gives you the probability of something happening. And so if you can turn that equation into a Taylor series polynomial, it's much, much easier and quicker for you to work with that too. So we actually use these a lot in my stat grad program too. All right, so we've got the series for cosine x. Well, if we want to look at cosine 2x, well, all I have to do is replace all of my x's with 2x. So now what I'm going to get is 1 minus 2 squared, x squared over 2 factorial, plus 2 to the 4th over 4 factorial x to the 4th, minus 2 to the 6th, and so on. So then what I want to do is, this is actually the same thing as saying 1/2 minus 1/2 cosine 2x. So if I multiply this polynomial by negative 1/2, look what happens to it now. So when I distribute the negative 1/2 across, two things are going to happen. The negative is going to flip all the signs to a different sign, but the 2 in the denominator is going to cancel with one of the 2's in the numerator. So you're going to see all the 2's in the numerator drop by a power. So I'm going to get negative 1/2 plus 2 over 2 factorial x squared minus 2 cubed over 4 factorial x to the 4th plus 2 to the 5th over 6 factorial x to the 6th, right? So all the signs flipped, and we lost a 2. And we're almost home. We only got to do one more thing. And the last thing we need to do to turn this expression into this expression is I need to add a 1/2 up front, right? So if I add a 1/2 up front, well, the 1/2 is just going to cancel this negative 1/2, and they're going to add to 0. Because it's literally going to be 1/2 minus 1/2 and all this stuff. So that's going to wipe that out. So I'm simply going to be left with this. So this is now the Taylor polynomial of degree 6, right, of sine squared. If I want to write it as an actual power series, well, we usually want to start from 0. And so what we have to do now is do a little pattern recognition. So what I want to do is I've got 2 raised to some stuff, and I want to make sure, right, that when I plug 0 into the exponent, I return a 1, because I want to get 2 to the 1 as my first term. So if you notice, all the 2's in the numerators are odd, right? They're 1, 3, 5. So if we write that as 2n plus 1, well, you can see when I plug in 0, I'll get 1. When I plug in 1, I'll get 3. When I plug in 2, I'll get 5. So that's going to count up all my odd exponents of 2. My factorials in the denominator are even. But if I try to write 2n factorial, well, 0 is going to give me 0 factorial. It's not going to return 2 factorial. So I actually need to use 2n plus 2 factorial. So now if I plug in 0, I get a 2. If I plug in 1, I get a 4. If I plug in 2, I get a 6. So it's going to count up all the evens. The signs are alternating. So we're going to have negative 1 to some stuff, right? So if I pick n or n plus 1, that usually I'll get the job done. Well, if I throw in n, right, and I plug in 0, I'll get that negative 1 will become a positive 1, and that'll make the first term positive, and that's what I want. If I plug in 1, it becomes negative, and the second term is negative, just like I want it to be. So the last thing we have to deal with is the x. Well, since the powers of x are the same as the factorials, if we've already figured out how to write 2, 4, 6 in the denominator, right, it's just going to be the same thing in the exponent. It's just not a factorial anymore. So now what we've got is the powers of x, right, match the factorial, 6, 6, 4, 4, 2, 2, and we've reduced the power of 2 by 1. So this would actually be the series written in series form of sine squared x. We could do a similar thing for cosine squared x, except instead of doing 1 minus 1/2, we would have done 1 plus 1/2 cosine 2x. And so that would have just tweaked things ever so slightly. So there's one more example I want to show you guys that you can do when you're multiplying stuff together. What if I want to write the power series for something like this? So if all you're multiplying up front, right, this isn't the same as sine x times sine x, okay? If all you're multiplying up front is x to some n value, right? But it's got to be like an actual constant, x squared, right? Well, what we can do is say that is the same thing as saying x squared times our series for cosine. And cosine is an odd function, so it returns all the odd powers. So all I have to do is distribute the x squared across, and all that's going to do is make all the exponents climb by 2, because you just add 2 to every exponent. So this would simply become x cubed minus x to the 5th over 3 factorial plus x to the 7 over 5 factorial. So notice that the factorials and the denominators didn't change at all because those were just constant numbers. But that's what you would do if you had a regular polynomial, right? You just distribute the x across. So if I had x squared times ln of x, I could just take the polynomial for ln of x and multiply it out. So let's see how to do that with the actual series. So we just found let's do one centered at 0. Yeah. Let's do arctan of x because I want to do something centered at 0. All right, so if we said, well, arctan of x was the series -1 to the n, x to the 2n plus 1, right, over 2n plus 1. And if I wanted arctan of x squared, then I would just plug in an x squared here and adjust the exponent. But if I want to know what x squared times arctan of x is, I can simply move the x squared into the summation. And remember, I'm allowed to do that because from the summation's point of view, x squared is just a constant because n is the variable of the summation. So the -1 to the n stays where it is, and I have x squared times x to the 2n plus 1 over 2n plus 1. And the rules of exponents say, well, if they have the same base, you add the exponents together. So the result would be -1 to the n, x to the 2n plus 3 over 2n plus 1. So there is, the idea here is when you're looking at these problems, and this was the trap, I mean, I fell into this all the time because I was a bit crazy taking too many classes. But in my mind, I would have been like, oh, I have to build this from scratch. And I would do product rule, and I would try to do all this craziness. And it was like you could literally just move the x squared inside. I was like really mad at myself when I figured that out. So this is the stuff that you guys, like I said, going forward, any of you that see Taylor series or any form of Taylor series again, this is the kind of stuff you need to be really comfortable with doing. Taking an existing series and manipulating it, like not starting over from scratch and reinventing the wheel. And just understanding your algebra rules and what you can do. All right, so that's it.